All right, team, I'm at the very end of chapter 7. You are so close to being done taking notes for this whole semester, which is very exciting. A few things for you to copy down. Remember, as always, guys, if I speak too fast, pause the vid and write down. Okay, I'm not trying to make some long-ass video for you guys, right? Just pause, copy stuff down, and then play so you can listen to my explanation, okay? Let's talk about symbols. I have tried to emphasize symbols several times throughout the notes packet, but these are things that you need to pay really close attention to. This is what's going to separate the good from the great, the 4s from the 5s. Okay, notation. Remember that X in algebra and in calculus stands for one number. X in stats stands for a random quantitative variable like shoe size, height, SAT score. Whatever the X is, it could be a different number for every single person, right? Therefore, when we average everybody's X's together from a sample, we get the sample mean. And we have to take samples of the same size if we're going to put them into a sampling distribution. And they all come from the variable X. So we've got a population that has a bunch of different X's. And if we take samples from all of the X's, we get a bunch of different X bars. Excuse me. And those are referred to as the sample means. So the sampling distribution, what is that by definition? That is the title of this chapter. The sampling distribution of X bar, and yes, we could also talk about P hat. That just means that we're sampling and coming up with a percentage or a proportion of a certain something that we're measuring for the sample. But the sampling distribution is a distribution. It's a dot plot. And it has every single possible combination from size n, whatever the size is. So a lot of times in class we did samples of size 5. That means every single dot on that dot plot comes from a sample of size 5. Sample could also be 10. We've done some pretty big samples in some of the problems we've talked about, but it includes every single possible value of X bar from all possible samples of size n. So every single possible combination, which includes millions and bajillions of dots, usually, right? Okay, anyway, so we've got mean of X and mean of X bar. Note those look almost identical if you're reading too quickly. Okay, the mean of X is just the true mean from an entire population. Okay, there's no X bar over that. That is from the entire population. But when you have an X bar, that means the mean of all the sample means in a sampling distribution. So remember the very beginning of the chapter, those 2 dot plots we drew on the very first page. I think that's really helpful. And make sure that you understand thoroughly the difference between a population distribution, every single dot stands for a person, and a sampling distribution. Every single dot stands for a sample mean or sample proportion if we're doing a proportions problem. Anyways, moving on. What kind of stuff do we need to do before we can just do the math? Okay, so look back at your FRQs that we've done. We did a couple of proportions problems. We did a couple means problems. Whenever you take a sample, so we did a sample of 10 women. We did a sample of 1,100, something that I can't remember off the top of my head. We did a sample of 1,500 first-year college students. Whenever you take a sample, you got to check stuff. The first thing that we check, and we need to make sure that we can separate whether it is a proportions problem. Are we dealing with a percentage? Or is it a means problem? Are we talking about like an average X value, not a percentage? So we need to be able to separate between the two. I've got like this chart here that I'm ready to kind of talk about, okay? You can see that I'm separating between proportions and means. But anyways, what I have is we need to first check to make sure it's random. Okay, always make sure whether it is a proportions problem or a means problem, no matter what, we have to make sure we have a random sample. We got to control for as much bias as possible. We talked about the issues if you were to take a sample using a convenience sample. If you were to use voluntary response in order to gather your information, that would that would inflate some of your numbers, right? That would make it pretty much not valid. We talked in class. It's got to be a random sample. What about making sure that the sample size is not too big? That's when we check the 10% condition. How do you do that? Take 10 and multiply it by your sample size, and you're just making sure that it's reasonable to assume that the population is bigger than this number. So look back through all of your FRQs we did in class. Whenever we took a sample, we had to make sure that the sample was not too big. That is the 10% condition. It's a good thing to put in your work, 10% condition met. When we're talking normality, is it okay to use normal CDF or table A? Usually we're not told that the distribution is normal anymore. We have to be able to check that for ourselves. So remember, if it's a proportions problem, I'm in the proportions column here. If it's a proportions column, we have formulas for that. NP and N1 minus P. They both must be bigger than or equal to 10. And if that checks out, that means your sampling distribution of P hat is approximately normal. Okay, but how do we do that for a means problem? Remember, for a means problem, we have X's. We don't have P's. So there are two different scenarios. Three technically. One of them we'll learn about next semester. Don't worry about it. But a lot of the problems we're told the population distribution, not sampling distribution, but the population distribution where every single dot stands for a person. If we're told the population distribution is approximately normal, that means the sampling distribution will also be normal. The heights of young women problem that we did applies that. Number two, can you apply the CLT? Do you remember how to apply the CLT? If your sample size is big enough, then that means even if the population distribution is not normal, you can apply the CLT and the sampling distribution will be normal. I'm going to talk more about this on the next page. And then option number three, what if neither of those applies? Like what if your population distribution is not normal and what if your sample is not big enough to apply the CLT? That means that we have to check plots. We will talk more about this second semester, but make a couple notes here. We can't use the CLT for proportions. For proportions, if you do this, you will lose points. Proportions, we have a formula to check. And that's the only way to prove normality of the sampling distribution. Over here, we do not have P's, so we have to look for other things. One of these three. Number three, you don't have to worry about yet. We'll get to that second semester. We're looking for this or this. Okay, these are the things you need to do, and you'll be asked to remember how to do on the test, okay? Let me talk about the CLT, the central limit theorem. That's what it stands for, CLT. And that applies when your sample size is bigger than or equal to 30. Again, this is not for proportions. This only applies to means, because for proportions, remember, we do this. Just wrote that on the first page. This only applies for means, the CLT. Why? Some of you might be wondering. I have some page numbers referenced here. On page 443, you will see this picture, and this was in the reading guide. And again, I expect that you have already read this, and this looks familiar to you. But let's take a look at this population distribution. Remember what a population distribution means. It means every single dot on this dot plot down here stands for a house, in this case. A house, what are the household earnings? Okay? And we have percentages here. That means that, just over 5% of households earn, I don't know, less than, what would that number be, $50,000 a year? We have some households, a very small percentage of households that earn $200,000+ a year. Every single dot here stands for a house. And you can see that the distribution here is right skewed, right? Definitely not normal. This is right skewed. Is that a problem? Not really, because if I take samples over and over and over again, in this case, I'm taking samples of size 100. So I'm sampling 100 houses from this right skewed distribution, and I am computing each X bar. And every time I get an X bar, I put a dot over here. And sometimes when I get an X bar, it might be less than. You can see the population mean is right here. That makes sense because it's right skewed, so the median is probably closer to the mode, and the mean is to the right of that because of all of these values that are dragging the mean up. We talked about that in chapter 1. But sometimes when I take a sample of 100 houses from here, I might underestimate the mean. And sometimes when I take a sample of 100 houses from here, I might overestimate the mean. But on average, if I do every single possible combination of size 100, the mean is going to be exactly where the population mean is. I'm guessing that's like 75,000, maybe 70,000, something like that. And look how beautiful and normal this distribution is. We could do this experiment with the Reese's Pieces applet that we talked about in class. But every single time you take a sample and you take a bunch of samples, in fact, all of the samples of size 100 in this case, then our sampling distribution will be normal as long as our sample size is big enough. Note that this is the mu. This right here I hand wrote in. This is the mean of all of the sample means. This is our sampling distribution. This is population distribution. Okay, so basically that is what I have kind of explained is written here. If we increase our sample size, standard deviation goes down. We talked about that. Why? We are gathering more information, therefore we have less variability. Think about the grade checks that we talked about. One person that has a bajillion grade checks is less impactful on a larger group of people, right? If I'm sampling 20 people, that outlier doesn't impact the average as much as it would in a group of 5. And here's our formula. Remember that the root n is in the denominator, and this is both for x, for means, and for proportions. The root n is in the denominator. Check your formula sheet. That means when this number increases, this number decreases. Here's the last thing I wanted to mention. On page 450, you can see a little bit more information about the CLT. So here is our population distribution. Definitely not normal looking, right? I don't remember what the context was of this, but we have like a chunk of people here, a chunk here, and a chunk here. And it doesn't matter what it is. But if I take a sample, and I'm trying to use the sample to estimate the average of this population distribution, what if I only take groups of 2, samples of 2? Think about how much one outlier would impact a group of 2. But maybe it would impact less a group of 10. And even less impactful on a group of 20. And even less impactful on a group of 50. So these statisticians have taken a distribution that looks like this. And they've kind of played around with their computer program. And they've taken samples over and over and over again. In samples of size 2, here is what the sampling distribution looks like. Does it look normal? No. 1, 2, 3, 4, 5. Definitely not a normal shape here. Okay, what if we increase our sample size to 5? Looks kind of sketchy still with all of these like humps, right? I wouldn't call that normal. Here for n equals 10, yeah, we're getting pretty normal now. And then they did n equals 25. Wow, it's looking a lot more normal. And they have decided on, as a rule of thumb, the CLT will be able to be applied if your sample size is 30 or more. So we have a couple 10s that we have to remember. The CLT is when n is bigger than or equal to 30. And this is just a little brief outline in terms of what you were supposed to read about on the reading guide that kind of explains the CLT, why it is what it is, what happens when you take samples. And that, my friends, in a nutshell, is your answer to the question why for the CLT that I promised I would give you. So thanks for watching. We are now done with the chapter. Let's submit these notes packets and let's crush this last test. Love you all.